So one of the other things that the fundamental theorem of calculus part 1 allows us to now work with are what are called integral defined functions. And these are functions that have an integral somewhere in it. It's not really mattering where it is, just somewhere in the function there's an integral, where one of the bounds involves that variable. So it's like when we were initially practicing the FTC part 1, where taking derivatives of integrals with x in the upper bound, the derivatives canceled out the integrals because they're inverse operations. Well, if we weren't taking the derivative, what's left is an integral defined function. And they're generally in the form of y equals the integral from some constant to a variable x of a function, and then adding on what the function value would be at the lower bound of our integral. Because if x is equal to k, my integral becomes 0, so this has to be that the value when x equals k. So what these tend to look like are things like, I know the derivative equals tangent, and when x is 3, y is 5, and I want to find out what y is. And we've seen similar ones like this when we were talking about finding antiderivatives before we learned about definite integrals. And it's just a more formalized structure for this. The idea of this is that here's the function that I'm going to be taking the integral of. I do want to replace the x with a dummy variable. Usually we end up using t, but it just can't be y or x. This is going to be my k, and this is going to be my f of k. Another way to think about it is that's also my plus c, because when we do an antiderivative, we have a plus c that we have to stick onto the end of our antiderivative. So when I'm figuring out what y is, the y has to be the antiderivative, which we now know is called an integral. My lower bound is going to be that 3. My upper bound is just going to be x of my tangent, and I'm going to use a dummy variable of t here with respect to t. Because my x is being used in my upper bound, I need a dummy variable in the integrand. And then plus the y value when x is 3 plus 5. So this just goes here. This is going here. And this goes here. And there is our integral defined function. And we can actually check this, because we know that to check an antiderivative, which is what we think this is, take the derivative. And since we now know how to do this, well, I have an integral, variables in the upper bound, constant in the lower bound. So all that happens is my upper bound replaces the dummy variable at tangent of x. Then derivative of 5 is 0. That checks out. That is our antiderivative. So if we did another example here, where my derivative is 9 over 7x times e to the x sine x, and I know that y is 4 when x is 17, well, this would be the integral. X is going in my upper bound. The 17 is my lower bound, because that's the x value they tell me about, of 9 over, and I'll use t again as my dummy variable. Then plus the 4, that's the initial y value they give me. Now, to kind of compare to how we did antiderivatives before, where we were finding general solutions and particular solutions, these are giving me particular solutions. They're just written in terms of integrals. So if I were looking at comparing the two ways, if I had derivative is 3x squared, and y is 10 when x is 2, and I want to find y, in other words, I want to find the particular solution. If I did it the old way, we said, well, antiderivative of 3x squared is x cubed plus c. And then to find c, I'm plugging in 2 for x and 10 for y. 2 cubed is 8, 10 minus 8 is 2. So I get that y is x cubed plus 2. In terms of how we're, this new way of doing it within an integral defined function, well, y would be my integral from 2 to x I'm going to use t again as my dummy variable, plus 10. Well, I can actually go ahead and say, well, my antiderivative is, I should say t, not x, is t cubed. So y would be f of x, the capital F of x minus capital F of 2. Subtract those, and then it's plus 10. If I plug x into this, I get x cubed. If I plug 2 in, I get 2 cubed. I still have that plus 10 cubed, not squared. 2 cubed is 8, so a 10 minus an 8, and I still get that y is x cubed plus 2. Both are correct ways of doing it. I will admit most people tend to stick with the old way when finding a particular solution for these, but we have to realize we may not always know the exact antiderivative, in which case using the integral defined function, so for example, this last example, here, we actually don't know the integral, the antiderivative of this. And so we don't have another, we can't actually evaluate this definite integral that we have in our function, so we have to leave it this way. And that is our function then.